Hi everybody, and welcome back to my lecture series on hardware for deep learning. We're in part 1, Introduction to Deep Learning. And what we learned in our last section was from artificial intelligence to deep learning. Now we're going into a bit more detail of training neural networks. So, we just discussed briefly about training neural networks, and we saw that what we have to do, for example, if we have supervised learning, is that we have a set of inputs and we run them through the network, and then we see what our error is and then drive that back through the network. So now we're going to go deeper into that. And first of all, what we need is a loss function, which describes the error. So a loss function tells how good our current classifier is. So if we take our example from before with our 4 pixels and our 3 classes, we showed there were a bunch of numbers in the weights, and we put our input through and we got some scores at the output, but we didn't know what to do with them. Well, what we do is we need to define the loss and show how the loss is going to work. Okay, so if we're giving a data set of examples, so xi are our examples, our inputs, for example, the pictures that we showed in our image classification problem, and yi, for example, are the labels. So we have this set of examples. The loss over the data set is the sum of the loss over the examples. So we're going to run all of these guys through, all of these inputs through, or this input vector through, and we're going to calculate the loss, which is some sort of function over all of the examples. And we're going to take the average. So we're going to take the output of our function. We're going to look at the expected label. We're going to calculate some sort of function over that. We're going to do it for all the examples, and we're going to take the average of all of them. That's basically the definition of loss. But there are many different functions that we could use here for this Li here. There are a couple of popular ones that are often used in machine learning. One of them is called multi-class SVM loss, and this is the definition of it over here. I'm not going to discuss multi-class SVM loss. You can see different tutorials and so forth on the web, or just search for it or look in literature. But we're going to discuss Softmax a bit more in detail, because Softmax has become very popular for image classification problems, among others. So let's look at the Softmax classifier, and we're going to take a few big words here, but then we're going to show some examples. So the Softmax classifier treats the scores, or the outputs basically, of our classifiers as unnormalized log probabilities of the classes. So what we're going to do here is we're going to say that the probability that y equals something when x equals a certain input is given by e to the power of sk divided by the sum of all of the e to the power of sj's that we had on all of our categories. Okay, where s is the function. So what we're going to do is we're going to take the our input. We're going to run it through the network. We're going to get some answer. We're going to raise that to an exponent, and we're going to divide for each category, and we're going to divide it for the loss we got for all the categories. We'll see that in a second. Okay, so what we want to do in our classifier to define our loss is we want to maximize the log likelihood, or alternatively, what we want to do is minimize the negative log likelihood of the correct class. So we're going to say the loss, according to some class I, is negative log of this thing over here for the class that was the right class. So let's see that complicated stuff in an example that will make it very clear. So we have our cat here, and we ran it through the network, and we got scores for the 3 different categories we had. The cat got a score of 3.2, the car got 5.1, and the frog minus 1.7. These are the unnormalized log probabilities. That's this e to the power of sk, where k is either cat, car, or frog. Now, we don't know if that is good or bad. So what we're going to do is we're going to, sorry, that's the sk. We are going to raise it to the exponent, so this is e to the power of sk. And then we're going to sum all of these guys together, and that's this sigma down here. And once we summed it together and we divide our e to the power of sk by the sum of the e to the power of sj, what we get is a normalization of the unnormalized log probabilities to the set of all the answers we got. Okay, so now we have these normalized log probabilities. This got 0.13, this got 0.07, and this got 0. Okay, what we want to do basically is we want everybody, we want our network to say that this is a cat and not to say that it's a car or a frog. What that means to say it's a cat is that we need to have only this guy be relevant. So what we're going to do is we're going to run a log just on the right class, this one. Okay, and we did minus log comes out 0.89. And what we want to do is minimize that. If our probability here was 1, that this would for sure be a cat in it, and everything else was 0, then we get 0 in our classifier, and there would be no error. It's probably never going to be a 1, but what that means is that we still have a way to go from 0.89 to bring this down to a 1, and that's the error for our set. So that is a softmax classifier, and that's the function that we're going to run on our classes during training. So how are we going to do this optimization? So we know how to calculate the classification. What are we going to do? So we're going to use gradient descent usually, or some type of gradient descent. Okay, what we have is we have lots and lots of parameters, all those weights, and we saw that just for our simple example in our neural network that was linear classifier that was calculating for Sci-Fi 10, we already had 30,000 weights, and in real neural networks we'll see that it gets to many millions, even billions of weights, and we want to reduce our loss to reach a minimum, but we have this very high number of parameters that we have to optimize. So what we can do is use gradient descent, which means we take the gradient, we look at the negative of the gradient, the opposite direction of the derivative, and as long as we go in the direction of the opposite direction of the derivative, we know we're minimizing our loss. Okay, so let's show this in a kind of example how we could do it. So what we could do is we could find the derivative of the loss function at the current point numerically. We know that the definition of a derivative is d to the fx x divided by dx is the limit when we take h and make it as small as possible, that we take the function with a slight increment of h, where h again is something very small, minus the result of the function at the current point, and we divide it by that small increment we took. And that we can do. So for example, what we do is we take our current weights. This is a vector, a long vector of all our 30,000 or however many millions of weights we have. Okay, and we figure out what the loss is. Then we go and we take one of these variables, we add a very small increment, like here 0.0001, and we again calculate what the loss is. So we had to calculate the loss twice for this thing. We take this loss and this loss, and we divide it by this guy, and we get our gradient for this first variable w0 or whatever this one is called. Okay, so so that is one way we can numerically go and figure out what our loss is. The problem with that is it's a lot of work to do that for each and every single one of our weights. As we said, we have a lot of weights, and if we have to do this calculation for every single one of our weights, it's going to be a lot of work. Okay, so instead of that, what we can do is we can find the analytic gradient. Now that seems to be really hard. If we know the analytic gradient, we can immediately just figure out what the gradient at the certain point is, and then we know what the negative of it is. But how do we find out this analytic gradient? Because that seems kind of complicated. Well, luckily we know how to do that for a lot of cases, and we use a process called backpropagation. So backpropagation, or we often call it backprop, is a way to find the analytic derivative and plug it into our model so we can easily train. Okay, so let's just give an example of how we're going to do this. Again, seeing an example usually helps, and we'll look at two examples. We'll start with a real simple one. So we have some sort of a function of x, y, and z, which is just simply x plus y times z. So what we're going to do is we're going to take that function and build a computational graph of very simple operations. Okay, so we have x, y, z are our inputs, and we see that what we do here is we take x plus y, okay, and that's this plus here, so this becomes x plus y, okay, and we take z and we multiply it by it, so this would be z times x plus y. We also will give it a name for this internal node, and what we have, so we say q is x plus y, and we also know that if we derive q by each of the variables, what we get. So if we do dq by dx, it's 1. And if we do dq, again, this is q by dy, we also get 1. So we know the partial derivative of q to these inputs. Okay, what about f? Well, we know that f is just q times z. Okay, we can do df to dq, right? And if we know that if the other one's a constant, so it just comes out d, and df to dz is q. Now, luckily, we have the chain rule. And the chain rule says that df, if we want to know the derivative of the entire function with regard to y or with regard to x, we can use the chain rule. So df to dy is just df to dq times dq to dy. Now, we already know what df to dq is, that's this, and we know what dq to dy is, that's this, so we can apply the chain rule, and quickly we see that df to dy is just z. Okay, so let's assume we have some current value in our network. Okay, this is the current x, the x vector that we're at. So x is minus 2, y is 5, and z is 4. What we're going to do is we're going to forward propagate these guys. Okay, so we're going to run inference. So inference is pretty easy. Minus 2 plus 5 comes out 3. Minus 4 times 3 comes out minus 12. Okay, now we're going to find the derivative of the output according to each input. Okay, so we know that the output is df to df is always going to be 1. Okay, we know, we saw before that df to dz is q. What's q? Q equals 3. So the derivative of df to dz is just 3. Okay, we saw that df to dq equals z. Z is minus 4. So the derivative right now at this point of df to dq is 4. And now we can find the derivative of df to dx and df to dy, which are df to dq times dq to dy. It's also z, so it's minus 4. And the same goes for x. It will also be z, which is minus 4. Okay, so we were able to backprop and find the derivatives at each of these points. So let's take a bigger example just to take a look at, and we have this more complex function. So we have f of w in x equals 1 divided by 1 plus exponent of minus w0 x0 plus w1 x1 plus w2. So let's take that whole thing and make a computational graph out of it. Okay, so what we have as our inputs, we have the weights and the inputs, right? w0 and x0, another weight and another input and another weight. Okay, so w0, x0, w1, x1, and w2 are inputs. So we have them here, w0, x0, w1, x1, and w2. What do? We multiply together w0 and x0, and that gives us a. So a equals w0, x0, right? And b equals w1, x1. Okay, and then we take these guys and we add w2 to them. So, so basically c equals a plus b equals w0 x0 plus w1 x1, and d equals c plus w2. I'm not going to write that whole thing out, okay, but it's this whole expression that's in the exponent. Okay, so what do we need to do? We need to have, we have a negative sign here, so we're going to multiply that by -1, so k equals minus d, and then we're going to raise that to the exponent, so g equals e to the negative of all this guy, and then we're going to add 1 to that, so h equals 1 plus e to this, and finally f equals 1 divided by all that thing. Okay, so we've broken down our long and strange function over here to a computational graph of very simple operations. Now all we have to do is find the derivative at each node. Okay, so we already said df to df is always going to be 1. Okay, now let's remember that the derivative of 1 over x is minus 1 over x squared. Okay, so then we can look back here and know what df to dh is. Df to dh is just going to be 1 over minus h squared. Okay, now what is the derivative of c, some sort of constant, plus x, which is c is 1 plus x? It's just going to be 1. Okay, so we get df to dg is going to be df to dh times dh to dg. dh to dg is 1, so it's going to stay minus 1 over h squared. Okay, now we're at the next node, and we know that the derivative of e to the power of x is just e to the power of x. So with the chain rule again, we're going to take d f to dk is going to be dg to dk times df to dg, which we've already found. So it's going to come out this e to the power of k times minus 1 over h squared. Okay, now minus 1, so df of some sort of constant times x is just the constant itself. So we're going to again apply the chain rule, and we're going to get negative what we had over here. So df to dd is 1 over h squared times e to the power of k. Okay, now what we have here is, again, x plus y. We have 2 inputs, and when we derive according to one of them, we get 1. All right, so that's going to be pretty easy. We're just going to get, for all of the inputs, the same thing over here, because it's just going to be multiplied by 1 according to the chain rule. Okay, next point, now we have a multiplication. So we have x times y. There are 2 different inputs. The derivative according to one of them is going to be the other. The derivative according to the other is going to be the first one. So what we're going to have here is we're going to take our derivative that we had here from the chain rule. Df to dA is going to be 1 over h squared e to the power of k, and to the one side it's going to be multiplied by w0, to the other side it's going to be multiplied by x0. And the same thing is going to go on this multiplication. So here we have w1 times what we had before. Here we're going to have x1 times what we had before. So we saw that we were able to back propagate all the way from the output to the inputs, and now we have an analytic expression that tells us what the partial derivative of the output to each one of these inputs is. So now we don't have to go and wiggle each of these inputs to see what the derivative at the certain place is. What are we going to do? Okay, we are going to take what we had before, and we're going to run inference. So we have 2 minus 1 minus 3 minus 2 and minus 3. Okay, we're going to run inference through the network. So 2 times minus 1 is minus 2. Minus 3 times minus 2 is 6. Minus 2 plus 6 is going to be 4. 4 minus 3 is going to be 1. Times minus 1 is going to be minus 1. E to the minus 1 is going to be 0.37. 1 plus 0.37 is 1.37, and 1 divided by that is 0.73. So we ran inference through this computational graph, and we got the current state at each one of these points. Now, we can go all the way back to the analytic expressions we have and just calculate them. But we see, for example, in the analytic expressions, what we need to have here are h and k. So we see here that h is 1.37 and k is minus 1, right? So, and we also want to say 1 divided by h squared e to the power of k. If we calculate that, it comes out 0.2. And then we can just multiply that by these inputs, x1, w1, x0, w0. And we quickly get our derivatives at each one of the inputs. Okay, so we immediately were able to calculate through backprop these things, and then we can advance in the negative of the gradient. Okay, so that brings us to a last term here, which is batch training. So the straightforward way to update the weights, as we saw according to our loss function, is that we should run inference on all the training examples and then calculate the average loss. Only after we calculated the average loss over all the training examples, only then we update the weights. But let's say we had over 1 million examples in our data set, for example in ImageNet. Are we going to run 1 million before we update the weight one time, and then we'll have to run it, thousands, millions of times in order to converge onto a minimum loss? That sounds like it's very, very, very costly. So instead, what is generally done is we use batches of inputs. We choose a batch size, and a batch size is a hyperparameter. One of the things that we just play around with in order to get a good number. So a batch size is we take some sort of n samples subset. So if we have a million inputs, maybe we only take 1,000 at a time or something like that, and we run them all through the network according to the loss that we get, with the average loss that we get. We update the weights, and we do it to the next 1,000 or n inputs. Okay, The batch size does have a lot of it affects the convergence and how good of an answer we get. So it's a hyperparameter. It's something we're going to play around with. There are many other hyperparameters. I didn't discuss them much in this lecture, but that is another one of these things that we have to play around with, and we can't exactly learn them. Okay, so again, for when we say batch, it means that we're going to take a certain number of all the inputs during training, we're going to run them through the network, we're going to calculate the average loss over all of those samples, and update our weights instead of going and running through all of the input set. However, when we discuss running through the full training set, we have a different name of this. It's called an epoch. So the difference between a batch and an epoch, a batch is part of an epoch. An epoch is if we run through all of the million or however many input samples we have. I just want to mention that there is another option to reduce training time, because training time can be very, very long. It can take days or weeks, or it depends on exactly what our model is and exactly what kind of things we're doing. But it takes a long time and a lot of expertise and luck to be able to actually train our models. So what we often do nowadays is use what we call transfer learning. That means that we already have some sort of a net out there. For example, AlexNet is a very popular net that won the ImageNet in 2012 and started this whole deep learning trend. Well, we have a set of weights that are already learned for them. So we can download that. In fact, a lot of the different libraries for deep learning already have a good good weights that were trained for AlexNet, for example. We can just download them, and now we can use a new training set. Let's say, we have a new data set. Let's say we don't want to do things in ImageNet, but something that also is image classification, just with different images. We can start from there and just run some more learning on it. So that's called transfer learning. Another thing we can do is actually take that, and instead of at the output use the categorization, we can add some more layers to learn some more. We can also stick the layers in different places, but it will save us probably a lot of time and probably get better accuracy if we start with something that was already taught and proven and shown. So those are the things I wanted to talk about in this lecture, and I just wanted to mention that this whole course is basically based on two courses that you can find on the internet. One of them is Stanford C231N. There are YouTube videos from 2017. It's a very popular course by Fei Liu's group at Stanford. The 2017 lectures are online, but you can also find the slides and so forth from 2019 and the lecture notes. Vivian Z has a great course that she goes around giving, and she most recently gave it at ISCA in 2019, and that can be found online as well. And she also wrote a tutorial about it called Efficient Processing of Deep Neural Networks, a tutorial and survey that was published in the Proceedings of the IEEE in 2017. The things I'm going to be talking to are heavily based on those two courses, so you're encouraged to go and take a look at them as well. Thank you, and we'll continue next time with convolutional neural networks.